I've got here a question from the 2023 Unit 3 paper, and we're looking here again at nuclear energy. And the first thing they're showing us on this question is question 5, so it's a little bit more complex than some of the other questions we get on the exam paper. And here we've got what's referred to as the binding energy curve. And as you can see, it rises very steeply. We get that funny little step. It rises to a peak here, and then it falls away to one side. We've got the nucleon number along the bottom, so these are the larger nuclei at this end, and these are smaller nuclei at this end. And then we've got the binding energy per nucleon in MeV up the side here. So this basically is energy against the amount of stuff inside the nucleus. And they want us to use the graph of nuclear binding energy to discuss why nuclear energy can be released by fusion and fission. They want us to talk about those processes with reference to this graph. So the first thing I'm going to say is I'm going to take it straight on. So it says describe fusion, basically. So what is fusion? Fusion is the joining, for want of a better word, of two smaller nuclei. Oh, helps if you spell it right. And it happens here. So this is fusion on the graph. Don't be afraid to write on a graph like this. What's fission? Fission is the opposite of that. It's the splitting of two lighter, what am I on about? Heavier nuclei. Helps again if you spell it right. And that's happening up here. So we'll write on that again here. So we've got fusion this way, fission this way. Now both of those, slide this one up a bit, both of those both increase. Can you see how the binding energy per nucleon is going up because the arrow is that way and this way? So both increase the binding energy per nucleon, and therefore they're more stable. Okay, lots of writing on that one, but there's marks just for drawing on the graph because we're showing that this stuff's doing fission, we're showing that this stuff here is doing fusion as well. We've described those two processes, everything is groovy there. Okay, so the next part of the question wants us to do a little bit of maths. Now there's lots of these sort of questions around, there's lots of number crunching to do here, so we'd best get into it, I suppose. First off, for a mark, they're giving us a clue here. They want us to define what is Avogadro's constant, and that's just a know it. You have to know this or you've got no chance really, can't work it out. It's the number of molecules in 1 mole, you know this from your chemistry, of atoms or a substance. Now reading that back, 1 mole of a substance. I don't know where that came from in there. Okay, so it's the number of molecules in 1 mole of a substance. So calculate the energy released by the fission of 0.0001 kilograms of uranium-235 in this reaction. We're going to use all of these numbers that are written in the question here. It's going to get quite number heavy. The first thing we're going to do is we're going to work out the difference between this side, the reactants, and this side, the product of this process. So we have to put these masses in and we need to be quite accurate. So we're going to do 235.04393 plus the neutron, which is over here, 1.00866. That equals, if you do it in stages, 236.05259. I like to work in stages because then I can see what I'm doing. So that's my left-hand side. Now my right-hand side is going to be a bit more complicated. I've got more stuff over here. So it's this one here, 97.91273 plus the technetium, 134.91645 plus, oh, careful, 3 of them, 3 neutrons, which are 1.00866. All that goes in the calculator. I've just pre-done these calculations so you don't have to watch me press the buttons. 5516. Okay, then what am I going to do? I'm going to do the left-hand side minus the right-hand side. So that's going to be, when you actually do those, take those two away from each other, you're going to end up with an answer of 0.19743. Don't forget, that's in U, atomic mass units. Okay, now what does it actually want us to do? Calculate the energy released. So that's actually a mass defect. So the first thing I'm going to do is turn that into MeV, which is a measure of energy. So into MeV. And to do that, I'm going to times by 931, which is this value here. And that's going to give me 0.80733 MeV is released. I might want that in joules. So next we'll times it by the joule conversion, which is, times by 1.6 times 10 to the minus 13. You might recognize this number. That's 1.6 times 10 to the minus 19, which is the charge of an electron. But because this is mega electron volts and we want it to come out in joules, not megajoules, we're going to do it by minus 13 instead of minus 19. We do that, again, that goes in the calculator and that outputs 2.94 times 10 to the minus 11 joules. Okay, feels like we're getting somewhere now, feels like we're almost finished, but we've got a couple of tricky steps to go. So we then take Avogadro's number, which is the number of uranium atoms there would be in a mole of uranium, and that's 6.02 times 10 to the 23. We're going to divide it by the mass of one uranium nucleus, or one uranium atom, I suppose, and that's times 10 to the minus 3. We're going to times that by the number of moles. Sorry, that's not an atom. That's the mass of a mole of uranium. We're going to times that by the number of actual kilograms I've got from the question. And that's going to output as 2.56 times 10 to the 21 nuclei. So that's how many I've got. Let's just check that back. Take Avogadro's number, divide it by the molar mass of uranium, times it by the actual mass of uranium you've got, and that'll give you the number of nuclei. You should always expect this number to be really, really big. Then we're going to take the fact that we had that much, 2.94 times 10 to the 11, sorry, I made a mistake here, that's minus 11 joules per nucleus of uranium. I've actually got that many of them, so I need to times them together. And that's going to give me 7.53 times 10 to the 10 joules. Lots of work for that one, 5 marks. In other questions, they might ask you to break this up, but because we're getting later on in the exam the exam paper, the questions are worth more marks, and as a result, you have to work by yourself rather than taking steps to get there. I hope that's helped. Go and find yourself another video, do some more practicing.